Hi everybody, welcome back to the next lecture on Multimediale Werkzeuge. Today about computer graphics or animation. So in computer graphics we have an artificial 3D object which is represented by a number of points in space and time for moving animated objects. So here are those points depicted. So these points in this case could represent, for instance, a circle. And these points are also called control points because they are given to span the object and also to move the object if it's, say, a movie. Yeah, so the essential point here is how do you interpolate those points in space and time, because for now they are just points and not a surface. Right? So we want to have a smooth surface that are spanned by those points. Or interpolation in time would mean interpolation from one so-called keyframe to the next, where we have objects at different positions and we want to make a smooth movement between them. Good interpolation allows us to use few points in space and time, also keyframes with longer time intervals, where the computer can be more efficiently interpolate in between frames, which makes creation of a movie more efficient. Yeah, so a very simple interpolation is linear interpolation. Right? And this results in polygons during interpolation in space. So we just take those points, those control points, and connect them by lines. That's the linear interpolation. So here's the example. We take those points and instead of a circle we now have this polygon because we just connected by straight lines. So this works well if you want to display polygon-like objects with straight edges and corners, but not so well if you have a circle. So the problem, this does not work well on smooth objects such as circles, ellipses, landscapes, peoples, meaning objects with smooth surfaces without edges and corners. For the smoothness of surfaces, a definition of how smooth a surface is helpful. For this we need gradients of the surfaces. Functions of variables, for instance u or v, are required to calculate a derivative or gradient and its continuity. So here you can see it. So we have the three coordinates of our point in space, x, y, and z. And these three coordinates are generated by a function of two helper variables. So u and v are helper variables, usually between 0 and 1. So they basically can be seen as a piece of a 2D surface. And then this 2D surface, using this function, is mapped into 3D. So this is a mapping of a two-dimensional plane in the variables u and v to the surface of our 3D object. Right? So this f is then doing the interpolation, and since this function is given, we can also compute how continuous it is. So in this way we can define continuity of surfaces. So we define C0 continuity as the continuity of the function itself. This means we have no surface cracks, the surface is continuously. Then we define C1 continuity as the continuity of the first derivative, which means we have no kinks in the surface. And the C2 continuity is defined as the continuity of the second derivative, which means we have no sudden change in curvature. So just wanted to move it in a little bit. Okay, so related to this is a geometrically defined continuity G0, G1, and G2, which is independent of the parameterization of u and v. But for our purposes, they are saying the same thing. So the goal usually is to have C2 or G2 continuity, which actually means including C0, C1 continuity. So we have continuity up to the second derivative. This is also important for temporal interpolation to avoid artificial robot-like jerky movements. Yeah, so a question, how do we get this continuity in interpolation? And for that we have to go back to the basics. What does interpolation actually mean? And this leads us to the Nyquist sampling theorem, because this is basically also interpolation. Right? We have samples. Nyquist tells us that we can sample a signal if it's low pass filtered first, and then we can sample it, and we can then obtain the original continuous version by low pass filtering those samples with an ideal low pass filter. So that's interpolation basically. So the Nyquist theorem also specifies how an interpolation is to be carried out with an ideal low pass filter with a cutoff frequency equal to half the sample frequency. Right? So here it depends on how many samples, how dense the sample grid is. The samples are our control points here for computer graphics. So here we are not in time, but in space, but we also have a density of our control points, which can be seen here. So here, this would be for Nyquist, this is the temporal axis. For computer graphics, this could be space or ordering of points. So vertically we have, for instance, the value of the x variable, and horizontally you have, for instance, a helper variable. Then you have those different points. Could also be time if you have a movie, right? You have keyframes, and here those keyframes, they have different positions of this point, for instance here in this axis. Yeah, given are those control points, and now we want to interpolate them in between. So Nyquist ensures that above the Nyquist frequency there are no signal components, which means the signal that we sample is very smooth to begin with. Right? So the function that we sample is very smooth. So this results in a minimum frequency of change, and which means we have a maximally smooth function. So this is also true for the interpolated curve, which has the same smoothness. Actually, Nyquist tells us that they are the same. The reconstructed interpolated curve is the same as the original smooth curve that we sampled, if both are the result of this ideal low-pass filter. Yeah, so the impulse response of the ideal low-pass filter is the interpolation function that we need to use, the sinc function. So here you can see the definition of the sinc function. Sinc of t is sine of pi t divided by pi t. And here I plotted a piece of it going from -4 to +4. And you can see at all the integer points on this x-axis here, we have 0 crossings, except for one. Here at the x-axis of 0, you have the function value of 1. So for the interpolation, basically we replace every sample by this sinc function. And then you can see the sinc function that's going through this sample here in the middle. It does not disturb the neighboring samples because we have those 0 crossings. And then if all the samples are replaced by those sinc functions, we simply add up all those sinc functions to obtain our interpolated curve. Right? It's that simple. So if our samples are located on the integer x values, they are not affected by the 0 crossings of the other sinc functions from the interpolation, which means interpolation goes through the samples or control points. Yeah. By filtering with the sinc function, we get a convolution with the sinc function, which leads to this substitution of the samples by the sinc function, which we can see here. So here we have the convolution. So A would be our sequence of samples, which you can see here. So this would be our A, and A consists of our sample, and each sample is located at the point of this Dirac pulse. So mathematically here it's represented by this infinitely narrow peak, which still has an area of 1 for the convolution to work. So, and then you can see here this convolution is simply this integral of the factor of those two functions, where this integration variable goes down in the second and goes up in the first. Right, and then we know, since we have the area of 1 for the Dirac in this A, basically what's left of B is the function value at the point where the Dirac appears. Right, so basically shift the Dirac at position t minus n, so here we have it at position n, becomes the sinc around n. So we would have sinc of t minus n as the result of this convolution. So here, this A is simply our sequence of control points as depicted in this picture here. Horizontally, we have time, for instance. Here we have the Diracs with those factors of x. And then we take the sequence and convolve it with a sinc function. And as a result, each of those samples will be replaced by those sinc functions in their place. So that can be seen here. Shifted Dirac convolved with a sinc function results in the correspondingly shifted sinc function. So now the sinc is centered over the sample position n. So this is what we then get. Here's the convolution with the sinc function, and as a result we have the superposition of the sinc function. Each sinc function takes the place of this sample. Yeah, so observe, we replace each sample by a correspondingly shifted and scaled sinc function and sum the sinc functions up. This can also be seen in this following picture. There the original samples are the small red circles, which you can see here, small red circles. And their sinc functions go through them. So here, for instance, the green curve is the corresponding sinc function. Yeah, whereas the other sinc function go through 0 at these points. The sinc function's sum is the black curve, which is indeed very smooth and goes right through the original samples, the red circles. So here you can see it. Here you can see this red circle and the green sinc function which belongs to it. Here this red circle and then this red sinc function which belongs to it. And then we sum up all those sinc functions, and the result is this black curve, which you can see here. And it goes indeed straight through all the sample points in a very smooth fashion. So no kinks, no jumps, very smooth. So this is very good. So the sinc function is an infinite polynomial, which means it is infinitely often continuously differentiable. And this also means the interpolated curve is infinitely often differentiable. So that's very good. It's even better than the so-called cubic splines, which we will see next, which can only be continuously differentiated up to the second derivative. But it turns out the cubic splines are actually more practical, as we will see next. So the problem here, the sinc function is great, but it's not so practical because it's infinitely long. That's why we have to look for alternatives. So we can use the convolution of our samples with the so-called box function as basis function for the interpolation. So instead of the sinc, we use this box function. So instead of the sinc function. So this is what we can see here. This is very compact. Yeah. It is very compact. It just has a non-zero value between x equals 0 and 1. So just on this narrow interval. So if we then use this to interpolate and replace every sample by this function, we get a box function in place of every sample. And as a result, we get a step-like function, kind of like a sample and hold. Yeah, which is easy to do, but it's not continuous because you have jumps here, right? The function is not continuous. So that's not good. This interpolation replaces every sample by the box function, and hence we obtain a piecewise constant function. But we have no continuity of the function value. To obtain continuity, we construct a new basis function by convolving the box function with itself, which results in a triangular shaped function, which we can see here. Right, we take this box function, convolve it with itself, and the result is this triangular function here. And this results in a continuous linear interpolation. Right? So now we replace every sample by this triangular function, which you can see here. And the result is that we connect all those control points by straight lines, right? Because triangles have straight lines. The edges are straight. So this leads us to linear interpolation. So again, very simple. So observe this function. This basis function is now wider and now contains two intervals, two integer intervals here, because of the convolution, right? So because of the convolution, we double the length, but it's still quite compact, right? So easy to do. Yeah, so the interpolation or basis function is 0 for the other samples, and this means the interpolated curve passes through our samples. We have C0 continuity, but no C1 continuity. We have kings, because the first derivative is not continuous. So this is what we still would like to have, right? We want to have C1 and C2 continuity. So the next step to obtain C1 and C2 continuity of the interpolation is basically to repeat the same trick again, right? So now we convolve the triangular function with itself. So H2 is the triangular function, we convolve it with itself, and we obtain H4. And this can also be obtained by 4 times convolving the box function with itself. And this results in the so-called cubic B-spline. And this is actually what's mostly used in computer graphics. Right? It's having the necessary continuities or desired continuities, and it's also very compact, still very compact. So in the frequency domain, this B-spline is a sinc function to the 4th power. Remember, multiplication in the space or time domain becomes the other way around. Convolution in the space or time domain becomes a multiplication in the frequency domain. Right? And since we know that the box function in the time domain is a sinc function in the frequency domain, then 4 times convolving the box function becomes the sinc function to the 4th power. And this also shows us why this works well, because the sinc function to the 4th power is a much better low-pass filter. Because the ripples in the passband are somewhat small number, but they become much smaller if we exponentiate them to the 4th power. So that means we have a better low-pass filter when we convolve the box function with itself. And this is also an explanation why this trick works. Convolution in time or space becomes a multiplication or exponentiation in the frequency domain, and this gives us a better low-pass filter. Not ideal filter yet, like the Nyquist Theorem would tell us, but it's becoming closer to the ideal low-pass filter. Right? So we don't have the optimum thing, but we're getting closer to it. So observe, this now corresponds to 4 convolutions of our box function with itself, and the result extends over 4 unit interval of our helper variable u, and hence we get 4 polynomials q. Right? So each unit interval will have its own polynomial, which we call q1 up to q4 of u, as depicted in the plot below. And this plot we make with this Python code. We compute the discrete B-spline basis function using convolution with Python by discretizing each unit interval into 10 steps. Hence we have a dt, a time step of 1/10. So this is basically a trick we don't really have continuous signals in Python, but we can have fine steps, and 10 steps is not particularly fine, but for our plot good enough. So that's what we do here. We define the box function as a sequence of 10 ones, so that covers our interval from 0 to 1 in time steps of 1/10. And then we obtain h2, the triangle, by convolving h1 with itself, multiplied here with the time steps dt, and the same for h4, convolving the triangular function with itself, multiplied by the time step. And then we can plot it, right, which you can see here. So here is our spline function. Here we have the x-axis from 0 to 4. And for each integer interval we have its own polynomial. Here in the first interval we have q1, in the next one we have q2, then we have q3, and finally we have q4. And you can also see it's nice symmetric, right, around 2. So it's like you have a mirror in the middle. So that also means if you have q1 and q2, then you obtain q3 and q4 by just mirroring q1 and q2 along the x-axis. Yeah, so in this way we get a very compact support just from 0 to 4 and 0 outside, in comparison to the sinc function, right? So the sinc function was infinitely long, which means our impulse response is quite short, length only from 0 to 4, and it can be represented by polynomials qi of u of third order, right, as we will see. Both makes it quite efficient for an implementation which is important for video coding purposes, for instance, or video coding or computer animation. So actually video coding is another application for this good interpolation, because there you need to interpolate also motion along time to get good prediction. Yeah, so the drawback is now that the B-spline does not go through 0 at the neighboring integer x values, as we saw, right? Unlike the sinc function, which was 0 at all the neighboring integer x values, this one stays above 0, right? So at x values 1 and 3 in the above plot, so I guess it was not really 10 and 30. As you can see here, 1 and 3, it's non-zero. It's like 1, looks like, you know, between 0.2 and 0.3. Right. Yeah, such that an interpolation with a simple convolution will not go through the original sampling points or values, which is not so good for image interpolation. Right. But actually for computer graphics it's not so bad, because you can still pre-process or shift the original points. Yeah, so or shift the original signal points first. Doesn't have to be an image, can also be points, so that such that the original samples are again obtained after the convolution with the B-splines. Yeah, so but first we have to find the polynomials q1 to q4. So how do we get them? To obtain these polynomials, we start with a fourth derivative because it is easy to compute, and then we just integrate 4 times to obtain the polynomial functions qi itself. So we start with the convolution derivative rule. So when we have a convolution, say of the box function itself, and we take the derivative, then this is the same as taking the derivative of one of the box functions and convolve it with the other one. So that's convenient, and you can easily see it by looking at the definition of the convolution of this integral. Right? If you differentiate this integral, only one of the two functions has actually the differential differential variable in it. And that's why you can draw the differentiation inside, and you get our differential rule. So you can just apply it to one of the two convolution functions. Yeah, and then we can extend it to 4 times derivative. The fourth derivation of the B-splines from our convolution is then this. Remember, our B-spline H4 is 4 times convolution of the box function, and if you take the fourth derivative, you can basically distribute the derivatives over all the box functions, and then we have just derivatives of the box function convolved 4 times with itself. And that's actually quite easy. The derivative of the box function is simply a Dirac delta in the beginning and a negative Dirac pulse at the end, right? Because in between the derivative is just 0. Yeah, and this then results into the fourth derivative of our B-spline function being just 4 times convolution of this pair of Diracs, right? And this is then the result. And here we can see we have different factors here, and these different factors come from several deltas which have the same shift. And when you convolve different deltas, you can see their shift adds up, right? Here in this way, and this is how you get several Diracs with the same shift, and this is how you get those factors here. You can also compute these coefficients in Python. Again, doing approximations. We simply represent the 2 Diracs from the derivative of the box functions as a sequence of 1 minus 1, right? 2 unit pulses instead of Diracs. And then we just convolve it, right? Here we apply convolve like we did above, just instead of Diracs we now apply it to unit pulses. And then here we get this result as our convolution once, and then we do the convolution again to get 4 times convolution, and these are the resulting factors then. You can see 1 minus 4, 6 minus 4, 1. And these are exactly these 4 coefficients. Yeah, so we now obtain the third derivative of our spline from this fourth derivative by integrating it first without an integration constant, because the fourth derivative does not need to be continuous. So here we see it, we integrate the fourth derivative to obtain the third derivative, and we get piecewise constant functions, because if the integral hits the first Dirac, it becomes area 1. Then here at the place of the next Dirac we have negative 4, so we have 1 minus 4, which becomes minus 3. Then we have plus 6 at the next position, so we end up at plus 3. Then we have minus 4 again, so we get minus 1 as a result. And then finally we add plus 1 and we get back to 0. So this is now the third derivative of our B-spline. So we are making progress. This is our third derivative. So now we can continue to integrate to obtain the polynomials q1 to q4. We start with q1 of u, starting at the just obtained third derivative. So we saw here, first interval, third derivative was 1. So this is what we got. And then integrated to obtain the second derivative. So integral of 1 is just u, right? Integrate again, we get u squared over 2. And integrate again, you get u to the third power over 6. And this is now our final polynomial q1 of u for the first interval. So that was easy enough. q2 follows in the next interval. But here we need to make sure that the second and first derivatives and the function itself are continuous across the interval boundary where q1 and q2 touch. at u equals 1 for the first interval and u equals 0 for the second interval. Right? So now we need to take care of the continuities. The second derivative of our function, of our polynomial, needs to be continuous across the boundary. So that means second derivative of q1 at position u equals 1 needs to be equal to the second derivative of q2 of the second interval at u equals 0. Similar for the first derivative and for the function itself. So we need to make sure that we have those continuities. So we start again with the third derivative. So here q2, third derivative was minus 3, as we saw in the beginning. And now we can apply the integration to obtain the second derivative. But now we need to include an integration constant c2 to obtain the continuity of the second derivative. So here c2. And now we need to do the checking across the boundary. So on the left hand side we have the second derivative of the first interval, and that was 1 for u equals 1. Right, when you look back here, here we had the second derivative of q1 was u, and if u equals 1, then it's 1. Right. So this is what we see here. This expression is 1, and if you plug in u equals 0 here on the second derivative, then this part disappears and c2 is left, so hence we have 1 equals c2. Right. So that's good. So now we have our second derivative as minus 3u plus 1. So that includes now the continuity. So now we can continue integration. The next integration constant is c1. So now we obtain the first derivative after integration with this integration constant c1. Again, to make sure that we have the continuity across the boundary, we get 1/2 equals c1. Right, so this is now the first derivative of the second interval. Then again, the function itself, integration again, now with the integration constant c0, plug it in on both sides and we get 1/6 is c0. So now we get c2 itself, q2 itself. This is now our final polynomial q2 of u. So now we have the first two intervals, and we saw that we have the symmetry, right? So we can just obtain q3 and q4 by mirror the lower polynomials by substituting u by 1 minus u, right? So this basically just mirrors them, flips them along the x-axis. And we do that by using an open source symbolic mathematics package called WX Maxima. So that's free for download and installation, very convenient. And I just plug in our polynomial where I replace, substitute u by 1 minus u, as you can see here. And then I tell it to rational simplify, and this is the result. Right, so this is now our final polynomial q3, and similar for q4, which is the mirrored q1. Again, here just substituting u with 1 minus u, rational simplify, and this is the result. And altogether, these are now our 4 polynomials. Right, so basically, now we can use them to interpolate between our sampling points. So we can now also write our spline function h4 as these piecewise polynomials. Right, and this is also how splines are defined. Splines are piecewise polynomials. Here, this spline function has 4 polynomials, 1 for each unit interval. Yeah, and for the interpolation, we saw we had a convolution, and this is then our convolution. So here this n is an integer index, which gives our control point positions. And t is a float variable, a continuous variable, which lets us arbitrarily interpolate between those integer control points. And this interpolation then is done using our spline function h4. And you can see here this function is shifted by 2, and that's simply because it has a maximum around 2. And if we don't have it, we would have a shift of our interpolated function by 2, since it's not centered around 0, like the sinc function. So this simply compensates for the shift. Yeah, this is what I just said. And yeah, since the spline function h4 has its maximum at n equals 2, we shift it accordingly by +2 in the above formula so that it's centered around 0. Now we can rewrite the continuous time variable t as the sum of an integer and not plus the float offset u on the unit interval. So just simplifying the formula, instead of having an arbitrary t, I have n naught as an anchor, and then having this helper variable u on the unit interval as of the interpolation variable, which tells us where on this coming unit interval we want to interpolate. Yeah, so for now this looks quite similar, except for this substitution here. So here this substitution. And now we can also simplify the range of the summation. Instead of letting n go over all possible samples, we limit it to the range where it's non-zero, which I did here. Right? When you look at h4, it only has 4 non-zero unit intervals, and that's why we can limit our summation range to those 4 unit intervals. Yeah, so now we can write the spline function h4 as an equation 1 with the 4 piecewise polynomials qi, and we can rewrite the sum in terms of those 4 piecewise polynomials. Right, this convolution sum, or more compactly here in this sum. Right, so basically the sum is the same as above, except that now I'm using these q functions here instead of the h4. So this allows a more convenient implementation, because in a computer you would have the 4 polynomials implemented. Yeah, so we see that we get the weighted sum of the 4 spline polynomials, each weighted by the corresponding sample value. So here we have those 4 spline polynomials, and you can see this as weighting each of those polynomials according to the sample values here, and this is on the integer grid. Right, this comes from our control points, which are given, and the values of our control points are the weights for our 4 polynomials qi. Right, so observe that again n naught and n are integer variables, and u is the float helper variables, and u is between 0 and 1 for the interpolated position. And observe that the u is indeed just appearing in those polynomials. Right, so they do the job of interpolation. Yeah, here's an example. Take some sample points or control points. 1, 2, 3, 4. Right, so this might be, for instance, a coordinate value in a movie. So then this might be some time index, say the frame index. We assume the other samples to be 0, and this is shown in the following picture. So here you can see it. The blue peaks represent the original values or control points from 1 to 0, and then they are 0 outside this range. And for interpolation, we simply replace each of those control points by our spline function. So here completely drawn as this bell-like function. So each of those sample points is replaced by those spline functions. And you can also see that the spline functions are not going through the peaks here. They're actually much smaller, and that's because the spline function at the peak just has a value of 2/3. So it's not 1. And you can also see that each spline function is not 0 at the position of the neighboring control points. That also means that the resulting curve at the position of the neighboring points will be influenced by this point in the middle, right? So this has the effect that the resulting sum, the resulting interpolation curve, is not going through those points but only close to them, as you can see here. So this red curve is the sum of all of them, and it's indeed nice and smooth, but it's not going through the original points, and actually it misses this one, the last one, quite a lot. And then here you can see, look at just this one interval between 0 and 1, and you can see here we have 1, 2, 3, 4 polynomials in this interval. So each point within this interval is the weighted sum of those 4 polynomials, Q1 to Q4. So this is what I just said. The blue peaks are the original sample values. The green and red lines are the weighted and shifted B-spline functions. The long red line is the sum of them. We want to interpolate a value at position u between 0 and 1 in the unit interval between sample points f0 and f1. We see that the sample points at both ends of this interval are connected to the peaks of the spline functions, the polynomials q3 and q2, so they have the most influence on the interpolated value, as expected. The 2 neighboring samples behind them still have some influence on the interpolated value, but only via the tails of the spline functions of q1 and q4. Hence, the considered to be interpolated interval has contributions from all 4 polynomials, which appear weighted by their sample values and add up, as in this formula, which is equation 2 with n naught equals 0. Right? So we again have this formula here, the weighting, and here you have the original function values at the grid, the integer grid values. And you can see we have the influence of 4 of them for the interpolated value. Right, and this also shows us that it's not going through the original sampling points. And this plot I just showed you was made with this code here. So you can actually try to recreate it by opening a terminal window. So I make it a little larger here. And I start Python 3. So this gives me the interactive mode, and then I just copy and paste. So copy and then paste it here. Return, and now it gives me this nice picture. Right. So again, you can see blue are the original sample points. Then green and red are each individual spline function, and here is the resulting sum. You can also see it's a little bit offset, and that's again by my precision of only 1/10 of the unit interval. Right here you can see each unit interval has 10 sample points. So this picture is not very precise, but it gives you qualitatively what's going on. Right. So in computer animation, actually the coefficients of the 4 spline functions are put into a basis matrix for easier calculation. So here you can see again the 4 polynomials and the coefficients, and you just take those coefficients and put them into a matrix. So each column of this matrix represents the coefficients of one of those polynomials. So the last one here is Q1, then the one before is Q2, Q3, and Q4. And I factored out this factor 1/6 coming from here so that you have simple integer values in the matrix. And if you then multiply from the left-hand side with a vector containing the exponents of u, then you just obtain the 4 polynomials. So this is just a convenient way to write those 4 polynomials in a computer, right? Because, say in Python, you can easily write this matrix as an array, and same here for these exponents of u. These polynomials are then applied to the control points in the convolution, and we actually get our C0, C1, and C2 continuous interpolation in space and time. Right here, back to our original example, we have our 5 points, and now hopefully we get something closer to a circle. So this again is not precise, it's more qualitatively. The point here is that the interpolated curve does not go through those points, but only close to them, right? But you can get the shape that you want by just shifting those control points somewhat, right? So that's basically to be observed in the design of 3D objects, that the control points are close to the interpolated surface but not necessarily on it. Yeah. Okay, so that's it for today. Thank you for your attention, and then let's see you next time. Bye bye.